Welcome back. In this video, what we're going to do is look at solutions to the sampling distribution worksheet that I gave to you to work on. In particular, this is the sampling distribution worksheet for the sampling distribution of the sample mean, the sampling distribution of the sample variance, and the sampling distribution of the sample standard deviation for random samples of size n equal to 2 from the population that has 5 values, the values 1 through 5, and the random samples are taken with replacement. All right, so that's going to be very important for us to consider here. And so we are going to be looking at solutions to this worksheet. So again, we have a finite population. The population size is, in this course, going to be represented by a capital N, and there are 5 values. And to keep things simple, so that we can focus on the concepts rather than calculations and things like that, we're going to just use the values 1, 2, 3, 4, and 5. All right, and so the first thing we need to do is to calculate characteristics of this population. In particular, we need to calculate the mean of the population. We also want to calculate the variance and the standard deviation of the population. Now remember, the mean of the population is a measure of location for that population, and then the variance and standard deviation are both measures of variation or dispersion associated with that population, the standard deviation being the positive square root of the population variance. And so let's do this first. So we see here, because this is a population, we're going to use the population formulas for the population mean, the population variance, and so forth. And we'll also denote these values using population notation. And so the population mean will be represented by a mu, lowercase Greek letter mu. And so the mean of this population is obtained by summing up the values in the population and then dividing by the number of terms in the sum, right? The population size. And so there are 5 population values. And so we see here that when we do this calculation, the population mean is equal to 3. All right, so very simple, but we know what it is now. Next, we're going to calculate the population variance. And the population variance will be denoted by sigma squared. And I'm going to use the definition formula for the variance of a finite population. And the definition formula is given by, or it's equal to, the average of the squared deviation of each value in the population from the mean of that population. And so we will have needed to calculate the mean first in order to calculate the variance, and we've done that. And so what we're going to do is take each of the values in the population in turn, subtract from each of these values the mean of the population, which is 3, and then square those differences or square the deviations, and then average those squared deviations. And so we have 1 minus 3 quantity squared, plus 2 minus 3 quantity squared, plus 3 minus 3 quantity squared, plus 4 minus 3 quantity squared, plus 5 minus 3 quantity squared. All right, and then we divide that sum by 5 because that is the formula for the population variance. We divide by capital N, all right? And so we get a value of 10 over 5, or 2, for the population variance. Okay, and then we take the square root of that, the positive square root, to get the population standard deviation. And so that turns out to be, 1.4142, rounded to 4 decimal places. Okay, and so those are the population characteristics that we're interested in this particular assignment. The mean, the variance, and the standard deviation of this population. Next, we want to consider taking a random sample of size little n equal to 2. All right, so in this course, capital N is going to be used to represent the size of a finite population, and lowercase n will be used to denote a sample, or the sample size from a population. And so we next consider taking a random sample of size little n equal to 2 from this finite population of 5 values. And again, we're taking these samples with replacement. All right, and so it's possible then to get the same value both times because we're sampling with replacement. All right, and so the question then is how many samples of size little n equal to 2 taken with replacement are there? All right, so let's look at the answer here. And it's very simple. By the fundamental rule of counting, there are 5 times 5, or 25 samples of size 2 taken with replacement. All right, and so for the first observation in the sample, there are 5 possible values, 1 through 5. And then remember, we're sampling with replacement, so we put whatever we got on the first sampling, we put that back, and we then pull out another observation or value, and we could get that same value back. So there are 5 possible values for the second observation as well. So there are overall 25 possible samples of size 2 taken with replacement from this population. Okay, now the next set of problems on the next page involve the sampling distribution of the sample mean. All right, so again, we're going to be looking at the sampling distributions of the sample mean, the sample variance, and the sample standard deviation in this worksheet, in this problem set. And we're also going to be looking at the to do this, we'll be looking at the distributions of those statistics. We'll also look at the joint distribution of the 2 observations comprising the sample as well. All right, but on this page, what we're doing is we're focusing on the sampling distribution of the sample mean. Now, you'll remember that the sampling distribution of a statistic is the probability distribution for that statistic. All right, so what we have to do here is to determine the possible values that the sample mean can take on across these 25 samples of size 2. And then we have to come up with the PMF, the probability mass function for the sample mean. And so keeping in mind that there are 25 possible samples, all right, you'll recall that I had this, this template. Let me decrease the size here a little bit. Okay, so I had this template that I put out there on Moodle to help you organize your work. And in fact, here is the actual template, empty. All right, so this is what was available on Moodle. And so what I wanted you to do in working this problem set is to use this template to organize your work. And so notice that we've got the space here. We've got enough rows for all 25 samples of size 2. All right, and the observations comprising the sample are going to be denoted by x1 and x2. All right, so these are the 2 random variables associated with or comprising the sample. And so then what I wanted you to do is to enter the possible values for x1 and x2 for all 25 possible samples. And then for each of those samples, calculate the sample mean, the sample variance, and the sample standard deviation, as well as the product of x1 and x2. All right, and so when you do that, this is what you get. So you have samples 1 through 25, and then you can see here that there are 5 samples where x1 is equal to 1, 5 samples where x1 is equal to 2, 5 samples where x1 is equal to 3, 5 samples where x1 is equal to 4, and then finally 5 samples where x1 is equal to 5. Likewise, there are 5 samples where x2 is equal to 1. You see that right there, right there, right there, right there, and right there, and then so on. There are 5 samples where x2 takes on each of the values 2 through 5 as well. All right, so these are the possible samples of size 2 taken with replacement from this population of 5 values. And then when you calculate the sample mean for each of these samples, you get this column of values. All right, when you calculate the sample variance for each of these samples, you get this column here. And then once we have the sample variances, we can just calculate the positive square root of those values, and that gives us the values in the sample standard deviation column. And then finally, we have the last column for the product of the x's, x1 and x2 values. All right, so from this, we can start answering questions about the sampling distribution of the sample mean. Okay, so let's take a look at the possible values for the sample mean. And by the way, notice I've got some summary rows down here. Let's ignore those right now. We'll come back to them in just a little bit. So if we look at the column for the sample means, the sample mean values, then we see that there are several values that x bar, the sample mean, can take on. It can take on the value 1, 3 halves, 2, 5 halves, and 3. All right, and then we see we've already accounted for the 3 halves. We've already accounted for the 2. Let's see here. It can also take on the value 7 halves. And then we have a value 4. It can also take on the value 9 halves. All right, and so the possible values that x bar can take on constitute the sample space for the sample mean x bar. All right, and so to construct the PMF, the sampling distribution, or the PMF of the sampling distribution for x bar, we have to list the possible values that x bar can take on. And notice that it can also take on the value 5. All right, so we see that down there. Okay, so I missed that before. Okay, so in this first column, I have included all possible values that x bar can take on for samples of size 2 from taken with replacement from this population. All right. Now, because of the way we're sampling randomly. Well, let me back up a second. Because we're sampling with replacement, like we said, there are 25 possible samples. And because we're sampling randomly, all 25 samples are equally likely. All right, and so they all have a probability of 1 over 25 of occurring. Now, what that implies then is that in order to calculate probabilities involving this sampling process, and in particular, for example, probabilities associated with x bar, all we have to do is just count the number of ways that that event can occur and then divide by 25. And so, for example, to find the probability that we get a sample, the mean of which is 1, all we have to do is to scan through here, and let me make this a little bit bigger now, scan through here and find those samples where the sample mean is 1. And we see here, as we scan through, that there's only one sample where that occurs. All right, and so the probability that x bar is equal to 1 is 1 over 25. All right, similarly, the probability that x bar is equal to 3 halves, that's going to be equal to the number of samples where the sample mean is 3 halves divided by 25. All right, and you can see here, again, as we scan through, that there are only 2 possible samples where that happens. This sample here, which we're calling sample 2, and then this sample here, which is sample 6. Okay, and so we see then that the probability associated with x bar being 3 halves is equal to 2 over 25. And we get the probabilities associated with these other outcomes in the sample space of x bar in the same way. All right, and so then the first 2 columns constitute the PMF for the sample mean for this sampling scenario. Again, sampling with replacement samples of size 2 from this population of 5 values. And so the first 2 columns answer question number 4. Determine the probability mass function of the sampling distribution of the sample mean for this situation. And that is given by the first 2 columns. And now notice here that the last row in this table, it's a summation row. For each of these columns, I'm adding up the values in those columns. In this first, so the summation for the probabilities, the probability column, that's just a quality control check to make sure that I've accounted for all the probability and I haven't accounted for anything more than once. And so you'll recall that the probabilities for a random variable across all possible values in the sample space for that random variable, those probabilities have to add up to 1. And so they do, right? And so from that standpoint, that's that verifies what we've come up with. Okay, next, we're going to compute the mean of the sampling distribution of the sample mean, all right? And so, in other words, we're going to compute the mean of this BMF right here. And the way we do that is to utilize this formula that I've got down here below the table, all right? And so we will denote the mean of the sampling distribution of the sample mean a couple different ways. I'm just including this notation so that you see it and get used to it. So we can denote this as mu sub x bar that I've got here, or as the expected value of x bar. And so let me zoom in a little bit. All right, and so you can see both of those notations, and I include them there just to show you and so that you can get used to that. Okay, so the way we calculate this quantity, this characteristic of the sampling distribution of the sample mean, is to use this formula here, right? So it's a weighted average, a weighted sum, and it's both a weighted average and a weighted sum, and I'll explain that in a second, but it's a weighted sum of the values taken on by x bar. So this sum, even though I don't indicate, I keep the notation simple, I'm not including the indices of summation, but essentially what we're doing here is adding up over the entire sample space for the random variable x bar. And so what we do here is take each of the values in the sample space of x bar, so 1, 3 halves, 2, and so forth, and then we have to multiply each of those values by the corresponding probability that x bar takes on that value. Okay, and so because so these are the weights. These probabilities are the weights that we're applying to or against the values taken on by x bar. And then because, remember, the way you calculate a weighted average is to first calculate a weighted sum and then to divide by the sum of the weights. Now the sum of the weights here, because we're dealing with a probability distribution, is 1, all right? And so if we calculate the weighted sum, then we're done because that's equivalent to calculating that weighted sum and then dividing by 1. So anyway, what we need to do here is we need to calculate these quantities, each of these terms in the sum, and then add up those products. And so what we're doing in this third column is calculating the product of each of the x bar values times its probability. All right, and so I've got those here expressed as a decimal, and then in this last row I do the summation. And so we can see here that the sum of the values in this column is equal to 3. And so what that tells us then is that the mean of the sampling distribution of the sample mean for this situation is equal to 3. Now, you'll recall that, let me scroll back up here to the very first page, that is equal to, that's the same value as the mean of the population. Okay, and so what we're seeing here is that the mean of the sampling distribution of the sample mean is equal to the mean of the population from which the sample was obtained. All right, and so that is this is the answer to question number 7. Is the mean of the sampling distribution of the sample mean equal to what the theory says it should be equal to? And the answer is yes, because you'll remember that whenever we're conducting IID random sampling, the mean of the sampling distribution of the sample mean will always be equal to the mean of the population that we're sampling from. And so that is, this is not a proof of that fact, but it's a demonstration of it. All right, and so we're verifying that that is in fact true for this particular example. All right, the next thing we need to do is to calculate the variance of the sampling distribution of the sample mean. And to do that, the formula that we have to use is given here, all right, that I'm pointing to. It's a weighted average of the squared deviations of each value that X bar can take on from the mean of its sampling distribution, which is mu sub X bar, but that's also equal to mu because mu sub X bar is equal to mu. I suppose I could clean this up a little bit to say mu sub X bar, and let me see if I can do that here real quick. Okay, so I cleaned that up a little bit, and that's what it, I prefer using this notation, but it was correct the other way as well, but I just want to make this more clear. All right, so what we have to do here is use this formula to calculate the variance of the sampling distribution of the sample mean. All right, and so again, what we're going to do is come up here, and I've got a column where I'm calculating each of the terms in this sum. Okay, and so what I've got, I'm going to take X bar minus the mean of its sampling distribution, which is 3, square that difference, multiply it by the corresponding probability that X takes on a value of 1, and so we get 0.16. Likewise, I do that for every other row, for every other value of X bar in its sample space, and I get the corresponding values in the last column, and then I sum those values up to get what turns out to be the variance of the sampling distribution of the sample mean for this situation. And so we see here that these values add up to 1, okay? And the question is, are the variance and standard deviation of the sampling distribution of the sample mean equal to what the theory says they should be equal to? Well, we'll answer this first for the variance, and then we'll talk about the standard deviation after that. Okay, so again, what does the theory say that the variance of the sampling distribution of the sample mean have to be equal to? Well, according to the theory, the variance of the sampling distribution of the sample mean should be equal to the ratio of the population variance, the variance of the population we're sampling from, divided by the sample size. In other words, it has to be equal to, it will be equal to, at least according to the theory, sigma squared over n. Okay, now remember that sigma squared was, for this population, was calculated to be 2. Note also that the sample size, little n, is equal to 2. All right, and so sigma squared over n is equal to 2 over 2, which is 1, and that is, in fact, the value of the sampling distribution of the sample mean for this situation. And so what we're doing here, again, is not proving that this result is true in general, but we're demonstrating that it's true for this particular situation. Okay. Now, if the variance of the sampling distribution of X bar is 1, then the standard deviation, which is the square root of the variance, will be 1 as well. And the theory says that the standard deviation of the sampling distribution of the sample mean will be equal to the standard deviation of the population you're sampling from divided by the square root of the sample size. All right, and so if the variance of the population is 2, then the standard deviation of the population is the square root of 2. And so, and then we divide that, according to this formula, by the square root of n, which is 2, so the square root of 2, and again we get 1. All right, and so what this, again, this is what the theory says to be the case, and this is what we're seeing based on this example. So again, what we're doing here is verifying that the theory holds, and it will, it always will, but it holds in this particular situation. Okay, let's see, we answered all those questions. Okay, next, on the next page, we're going to be investigating the sampling distribution of the sample variance. And to do that, we're going to do very similar things that we did on the previous page for the sampling distribution of the sample mean. In particular, we're going to determine the PMF of the sampling distribution of the sample variance. We will compute the mean of the sampling distribution of the sample variance, and then we will consider the question, is the mean of the sampling distribution of the sample variance equal to what the theory says it should be equal to? Now, we're not interested in this situation right now with the variance of the sampling distribution of the sample variance. All right, we're focused in terms of the sampling distribution of the sample variance, we're interested in the mean of its sampling distribution. All right, so let's take a look at this next page. And so again, determine the PMF of the sampling distribution of the sample variance. And so if I go back to this filled out template that has all 25 samples, and for each of those samples of size 2, I've calculated the sample variance. All right, and so you see that the possible values for the sample variance consist of 0, 1/2, 2, 9/2, and 8. And so if we go back here, you'll see that I've got those values listed in the first column, right? So this first column, again, is the sample space for S squared. And then to calculate the probabilities associated with each of these, we just have to go back and count the number of times that a particular value shows up in this column and then divide by 25. And so the probability that the S squared takes on the value 0, well, we see that happens 1, 2, 3, 4, 5 times. And so the probability associated with that would be 5 over 25. And we get probabilities for the other values in the sample space in the same way. Notice again that I am calculating the column total for those probabilities, again, just as a quality control check to make sure that I've accounted for all the probability and haven't duplicated anything anywhere along the line. Okay, then the next thing we need to do is to compute the mean of the sampling distribution of the sample variance. And so we again calculate a weighted average of the values taken on by S squared. The notation for the mean of the sampling distribution of S squared. Again, there are two ways we can denote this. The first, mu subscripted with S squared, so the mean of the sampling distribution of S squared. All right, let me make that a little bigger here. You can see it. And but we can also represent it this way, or denote it this way, the expected value of S squared. Now again, this is a weighted average of the values taken on by S squared, okay? And the weights being the probabilities associated with the particular values of S squared. And so this summation here is the formula for the expected value of S squared, or in other words, the mean of the sampling distribution of S squared. So again, what I'm doing to organize my work is to have a third column out here where I have the terms in the sum, S squared times the probability that cap S squared, the random variable, is equal to the observed value, little s squared. And so I'm just taking the product of these two, the corresponding values from these two columns in each row, and listing them out here, and then calculating the column total. And so I get 2 for the mean of the sampling distribution of S squared. All right, and so we then consider the question, is the mean of the sampling distribution of the sample variance equal to what the theory says it should be equal to? And again, the theory says that the mean of the sampling distribution of S squared, now remember, let me just stop here for a second. Remember that when we calculate the sample variance, the denominator is little n minus 1, right? It's 1 less than the sample size. And the reason we do that is to make that estimate of the population variance an unbiased estimator for the population variance. And what it means to be unbiased is that the mean of its sampling distribution is equal to the parameter that we're estimating. So in this case, the parameter we would use, or that we would estimate by S squared, is sigma squared. And so what ought to happen here, the theory says that if we calculate S squared in this way, then the mean of its sampling distribution should be equal to the population variance itself. And so you'll recall that the population variance is 2. Well, that's the mean of the sampling distribution of S squared as well. And so we see that it is in fact equal to the population variance, which is indeed what the theory says it should be. So, and let me just emphasize something here. We're not saying that the random variable is always equal to sigma squared. In fact, it's obvious that that's not the case. In fact, in this example, there's only one value in the sample space for S squared that is actually equal to the population variance. So from one sample to another, and in fact, if I go back here, this is perhaps more easily seen, we can see that from one sample to another, the sample variance varies, okay? But the mean of those values will be equal to the variance of the population, all right? And that is what the theory says should be the case. Okay, so let's look at the next page. On this page, we're going to be considering the sampling distribution of the sample standard deviation, all right? And we'll be answering similar kinds of questions that we did for the sample variance, but with one additional question. Okay, so let's take a look at the solutions for this. Let me zoom out just a little bit. All right. So, considering the sampling distribution of the sample variance, the sample standard deviation. Okay, so first determine the PMF, the probability mass function of the sampling distribution of the sample standard deviation. And so I've got that here in the first two columns, the PMF of the sampling distribution of the sample standard deviation, which in this solution key I'm denoting by S, which is the typical notation, is given in the first two columns of this table. All right, and so again, how do I get that? Well, how do I get the sample space? How do I get the probabilities? Well, I just go back to my table, right, where I calculated the sample standard deviation S for every value for every possible sample. Let me correct my statement there, for every possible sample. And I see the values that are taken on by the sample standard deviation. And I've represented them perhaps a little bit differently here, but these are the unique values that are taken on by the sample standard deviation. And then I get the probabilities by counting the number of times that a sample had a standard deviation of 0 and dividing that by 25 and so forth. And notice that these probabilities are the same probabilities that we had for the sample variance, because the sample standard deviation is just the square root of the sample variance. And so the values in the sample space here are just the square root of the values in the sample space for the sample variance. Okay, so the first two columns give us the PMF for the sampling distribution of the sample standard deviation. And then the next question asks us to compute the mean of the sampling distribution of the sample standard deviation. And so again, I've got two ways that I'll denote this, as mu sub s in this case, and also the expected value of s. And again, this is defined to be this weighted average of the values taken on by the sample standard deviation, the weights being these probabilities. Okay, now, so again, what I've done is added a third column, right, where I can to help organize my work. And so I'm just taking products of the values in the first two columns for each of the 5 rows, and then putting those values over in this last column, and then I add those up, all right, to get this sum, and that gives me then the mean of the sampling distribution of the sample standard deviation. And it turns out, rounded to 4 decimal places, that's equal to 1.1314. Now, question 14 asks, is the mean of the sampling distribution of the sample standard deviation equal to the population standard deviation? If not, is it smaller or larger than the population standard deviation? Okay, so the mean of the sampling distribution for the sample standard deviation in this particular situation is 1.1314. That is not equal to the square root of 2. You'll recall that the square root of 2 to 4 decimal places is 1.4142. So that is not equal to the mean of the sampling distribution of the sample standard deviation. Okay, and so because of that, the sample standard deviation is not an unbiased estimator of the population standard deviation. That is in contrast to the mean, the sample mean, being an unbiased estimator for the population mean. And again, that's the case because the mean of the sampling distribution of X bar is equal to the mean of the population we're sampling from. Likewise, the sample variance, the version with n-1 in the denominator, is also, it's an unbiased estimator of sigma squared, again because the mean of its sampling distribution is equal to sigma squared. However, the sample standard deviation does not have this feature. It's not an unbiased estimator of the population standard deviation. So that's just the reality of it. All right, and we choose to calculate S squared in a particular way to make it unbiased, but when we take the square root to get the standard deviation, the transformation we're applying is not a linear transformation. Because of that, S is no longer an unbiased estimator for the population standard deviation. Okay, and then on the next page, consider the sampling distribution of X1. And then after that, we look at the sampling distribution of X2. Now, these are fairly straightforward, and I'm including them really for what we're going to do subsequently. And I'll show you that in just a little bit. But let's just take a look at this. We'll look at this one, the sampling distribution of X1, fairly carefully, and then the calculations for the sampling distribution of X2 are the same. Okay, so first, determine the PMF of the sampling distribution of X1. Compute the mean of the sampling distribution of X1, and then compute the variance and standard deviation of X1. Okay, so going back to this table, let's look in the X1 column, and let's look at the possible values that are taken on by X1. Well, we see that obviously it takes on the values 1 through 5. Okay, and so I've got 1 through 5 listed here as the sample space for X1. In addition, the probabilities associated with each of these, we see from this table, but it's intuitively, it should be intuitively clear to us that the probability associated with each of these possibilities is 1/5. Okay, so the first 2 columns give us the PMF for the distribution of X1. Then we want to calculate the mean of that distribution. That's given by this weighted sum here, weighted average. And so I've got a column for that calculation. And so I'm multiplying corresponding entries in the first 2 columns for each row, putting those values here, and then adding those values up, and we get 3. So the mean of the sampling distribution of X1 is 3, which is the mean of the population. Well, that's exactly what it should be, because X1, it's a single observation coming from this population. All right, and then similarly, to calculate the variance, we're going to calculate this weighted average. weighted average of the squares of the deviations between each value taken on by x1 and the mean of its sampling distribution. And so the mean was 3, and so we subtract 3 from each one of these, square the differences, multiply by the corresponding probabilities. And when you do that, you get this column of values here. And then when you add that up, all right, then you get a value of 2, and that is the variance of x1. Well, again, that's the variance of the population, and it should be clear that when we're talking about the distribution of a single random variable from some population, it's going to be equal to that population. So there's really no surprises here, but I wanted to just show you and do this calculation because we will need, in particular, we'll need the value of the variance of x1 later on. And I could have just told you it was 2, and you know, it probably would have been extremely clear to you, but just in case it wasn't, I wanted to show what I'm talking about. Okay, and then the next page has the solution for this, these questions involving the sampling distribution of x2. All right, it's the same type of calculation, so I'm not going to look at this in detail. Okay, so let's look at the next set of questions. And so on page, let's see, this is page 7, okay, we are asked to consider the joint sampling distribution of x1 and x2. And the reason we're doing this is we're answering the question, are x1 and x2 statistically independent or are they dependent? Now, another word for this would be stochastically independent. So stochastically independent or statistically independent, you'll see both of those terms used for this concept. And so in order to answer this question, we need to look at the joint sampling distribution of x1 and x2. And so that's what we're going to look at next. Okay, so let me scroll down here. All right, so here is the joint PMF, the joint sampling distribution for x1 and x2. And so you'll see here in this column, I've got the values that x1 takes on, 1 through 5. And then my columns correspond to the values that are taken on by x2, again, taking on the values 1 through 5. Each cell in the table corresponds to a combination of x1 and x2. So for example, this cell here, the cell itself, not the value, but the cell, corresponds to the outcome where x1 is equal to 1 and x2 is equal to 1 as well. This cell down here that I'm pointing to, again, not the value in the cell, but the cell itself, corresponds to the outcome where x1 is 5 and x2 is 2. Now, based on this table here, right, based on the fact that we are sampling randomly, all 25 possible samples are equally likely, okay? And again, each one of these rows corresponds to a cell in the body of this table, okay? And so there are 25 cells in the body of this table, each one corresponding to one of the 25 possible samples. And we said earlier that because we're sampling randomly, each of these possible samples has the same probability, and in particular, that probability is 1 over 25. And so that is where we're getting these values here. Now, are x1 and x2 statistically or stochastically independent, or are they dependent? Well, what we can note is that for each x1 ranging from 1 through 5, and for each x2 ranging from 1 through 5, so if we consider a particular x1 and a particular x2, we see that the probability that the random variable x1 takes on that value of little x1, and then this column is read and the random variable x2 is equal to the particular value of little x2, we see that whatever the values for x1 and x2 are, that probability, that joint probability, is 1 over 25, because all of these are 1 over 25. Well, note that I can write 1 over 25 as 1 over 5 times 1 over 5, right? Well, that's convenient for us to realize, because the probability that x1 takes on, the random variable x1 takes on the value little x1 is 1/5, right? That's one of the reasons we looked at that sampling distribution for x1. Okay, so this 1/5 right here is this marginal probability, and then this 1/5 corresponds to this probability involving x2. Now, the definition of statistical independence is that in order for two random variables to be stochastically independent or statistically independent, for every value of x1 and x2 in the sample space, this joint probability has got to be equal to the product of these marginal probabilities. And you can see here that that is in fact the case. And so it follows then, by the definition of statistical independence, that in this situation, x1 and x2 together, they are statistically independent. They're independent of each other. Okay, so that answers that question. And let me also say that this result follows from the fact of the type of sampling. In fact, you'll remember that this is what we're covering here so far in the course is called IID, random sampling. Independent and identically distributed random sampling. So the first I there corresponds to independent. And this is exactly what that means. All right? That the random variables comprising our sample are independent, statistically independent of each other. Okay, so what we've done here, obviously, and again, we've not proven that of this result in general, but what we've done is demonstrate the truth of that general result for this particular situation. Okay, and then finally, the last three questions: compute the covariance of x1 and x2, compute the correlation between x1 and x2, and then are x1 and x2 correlated or are they uncorrelated? All right, and so let's do the calculation. And so, but first, before doing the calculation, let me just point something out and we'll see if the result holds. Because we've just shown, we've determined that x1 and x2 are in fact statistically independent. The theory says, that what should be the case is that the two random variables x1 and x2 should have a covariance of 0 and a correlation of 0. Okay, now let's see if that's the case. So the covariance of x1 and x2, which is denoted using this notation here, right, the covariance of x1 and x2 is equal to, and this is not the defining formula, this is a computational formula. It's given by the expected value of the product of x1 and x2 minus the product of the expected value of x1 and the expected value of x2. Now, we found the expected value of x1 and we found the expected value of x2 several pages back. We have not yet found, at least we've not talked about, the expected value of x1 times x2. Now, where can we find this? How do we do this calculation? Well, one way to do it would be to take the joint PMF and to calculate the weighted average over all values of x1 and x2 in the joint sample space, multiplied by the corresponding probabilities. All right, but and we could do that, but we've actually, well, then add those values up. We've actually already done that. All right, and let me show you where we did it. We did it in this table here. All right, because you'll notice that that's why we have this last column. All right. We have x1 times x2, all right, so the product of the values in these two columns, putting those values in this column. And then, look, once we have this column, all we have to do to get the expected value of x1 times x2 is to calculate the mean of the mean of that population of 25 values, all right, and so that is equal to 9. Now, let me just take a moment to convince you that that is equivalent to the other method that I just discussed. And to do that, what I want to do is let's go back and consider the mean of the sampling distribution of x bar, right, first. So let's go back here, scroll back, Okay, so we found the mean of the sampling distribution of the sample mean, and we used this formula here, right? So this is that weighted average. And we found the mean of the sampling distribution of x bar to be 3. Well, let me just say that a distribution like this is really a summary or a condensation of the values in this list, and in particular, this column of values, all right? It's just a summary of these values. We could get the same value for the mean of the sampling distribution of x bar by just averaging these 25 values in this column. And when we do that, we get 3, okay? Notice that we could also get the variance of the sampling distribution of x bar by calculating the population variance of the values in that same column. So if I calculate the variance of the values in this column using the population formula, I get 1. Well, those are the exact values that I got using these other formulas. Similarly, if we look at the sampling distribution of the sample variance, we found the mean of its sampling distribution to be 2. Okay, well, let's go back and look at this column of values. I could get the same result by just calculating the mean of the values in this column, right? Because the values, the 25 values for s squared in this column constitute the population of values that s squared can take on. And the mean of the column is 2. So again, it's the same exact thing. And then finally, we could do the same thing for the the sampling distribution of the sample standard deviation, finding the mean of its sampling distribution. All right, we found that the mean of its sampling distribution using this formula was 1.1314. Well, that's the mean of this column of values, right, that S takes on, 1.1314. So, with that in mind, we can find the mean of the sampling distribution, the expected value of x1 times x2, by just calculating the mean of the values in this column, and that mean is 9. Okay, so having said that, let me scroll back down here to the bottom. All right, and so we have everything we need now to calculate the covariance of x1 and x2. And so the expected value of the product of x1 and x2 is 9. The expected value of x1 was found to be 3. The expected value of x2 was found to be 3. And so we have 9 minus 9, or 0. So the covariance of x1 and x2 is 0. And then once we have the covariance, we can find the correlation. You'll remember that the correlation between x1 and x2 is equal to the covariance of x1 and x2 divided by the square root of the product of the variances. Now the variance of x1 was 2, the variance of x2 was 2, all right? And since both of those are non-zero, all right, then we see that the correlation is well defined, and in particular, it's equal to 0. So again, we noted that up here, that because x1 and x2 are in fact statistically independent, we showed that in the previous problem, the theory says that the covariance and correlation between those two random variables must necessarily be 0. Well, we've shown that to be true. We haven't proven the result in general, again, but we've demonstrated that this general principle, this general result, is in fact true. Okay, so those are the solutions to the problems on this worksheet, and the reason we did this is because we've demonstrated, we've done this in the context of IID random sampling. Again, independent and identically distributed random sampling. We're going to do a similar kind of exercise when we get into some other kinds of sampling techniques. So for example, simple random sampling. And we're going to investigate properties of estimators and relationships between random variables in the context of that mode of sampling. And I think it will be very helpful to be able to relate those results back to the results that we got in this worksheet for IID random sampling. We'll be able to contrast some results as well. So that's all for this video. And if you haven't gone through this, make sure that you do do the work, do the calculations, all right, and make sure that you can do it. You understand everything here.